term compliant motion applies to a variety of manipulation tasks, such as inserting a peg into a hole, placing an object on top of another one, driving a screw, opening a door, following a contour, etc. In all these tasks, contact forces or tactile stimuli modify or even generate the position trajectory of the robot end effector. Two kinds of compliance are distinguished. Active compliance or active force feedback occurs if the robot control system is capable of measuring contact forces and is programmed to react to these inputs. On the other hand, passive compliance or passive force feedback occurs if the compliance is due to passive compliance present in the manipulator structure or in the position servo. This video film shows several applications of active compliant motion. However, a certain amount of passive compliance is always required, as will be explained later. Although the term compliant motion is usually associated with force or tactile feedback, it can also be used in a broader sense with respect to other types of sensory feedback, such as proximity or vision feedback. This film, however, will be restricted to compliant motion involving force feedback. To perform compliant motion, two basic elements are required, namely 1. A 6-component force sensor which, after some processing, provides information about the actual contact force, and 2. Adequate programming and control techniques which allow the incorporation of force control into the robot control system. In our experiments, we used a 6-degree of freedom force sensor mounted between the robot end plate and the tool. The sensor measures, almost simultaneously, 3 forces and 3 torques. Forces up to 200 Newton and torques up to 20 Newton meter are measured with an overall accuracy of 2%. The force acquisition speed equals 20 kilohertz. For every compliant task, a special coordinate frame exists in which the task can be expressed in terms of velocity and force control directions. This frame is called the task frame. Consider, for example, the turning of a crank. In the coordinate frame, shown at the center of the crank, the task is expressed by specifying a desired rotational velocity around the z-axis and by specifying desired zero forces and torques in the other 5 directions. The choice of the task frame is not always unique. Indeed, in this particular example, one might as well draw a coordinate frame at the center of the robot gripper and express the task by specifying a desired translational velocity along the x-axis and by specifying desired zero forces and torques in the other 5 directions. As a second example, consider the tracking of an unknown 2-dimensional contour. Here, the task is expressed by specifying a desired velocity along the contour tangent and by specifying a desired contact force along the contour normal. However, this does not completely describe the task, since the position and orientation of the contour, and hence the position and orientation of the task frame, is not known in advance. Indeed, in this example, the actual position and orientation of the task frame have to be inferred from the interaction between contour and robot end effector. This ambiguity is solved by introducing a third type of direction in the task frame, the so-called tracking direction. In a tracking direction, The robot controller has to track the actual position or orientation of the physical task frame. For the contour tracking problem, the complete task description therefore consists of a desired force in x direction, a desired velocity along the y-axis, rotation around the z-axis of the task frame is a tracking direction, and finally, desired zero velocities are specified in the 3 remaining degrees of freedom because of the two-dimensional nature of the task. As a conclusion, every compliant task can be expressed in terms of velocity control directions, force control directions, and tracking directions. The control method used is based on the following ideas. 1. Consider the robot as a closed-loop positioning device. 2. Close an external servo loop around this positioning system for every degree of freedom in the task frame. For the force control degrees of freedom, this means that force errors occurring in the task frame are first transformed into velocity or position commands. Then, these commands are transformed from the task frame to joint space, where they are input into the positioning system. This control technique requires the presence of a passive compliance in order to avoid large limit cycles caused by the finite position resolution of the positioning device. The exact value of this compliance is irrelevant, but the order of magnitude is important, since the compliance, together with the position resolution of the robot, determines the achievable force resolution. In order to perform compliant motion experiments using a stiff robot with low position resolution, a general-purpose 6-dimensional compliance structure was designed such that the elements of the compliance matrix have a suitable order of magnitude. The experiments are performed using an electro-hydraulic Cincinnati T3 robot. The position accuracy of this robot is around 1 millimeter, and therefore the additional 6-dimensional compliance structure described earlier is required. The external control loops are realized in an HP 1000 A700 minicomputer. The first task consists of tracking an unknown 2-dimensional contour with a constant velocity of 15 mm per second and a constant contact force of 50 Newton. As explained before, the desired goal in each of the 6 task frame directions completely describes the task. In order to show that the control scheme used is very robust with respect to disturbing forces, a grinding or deburring operation is added to the tracking problem. There are 2 phases. The approach phase, in which the contact force between tool and workpiece is built up, and the actual tracking phase. The task specification for both phases is very similar. The forces shown are displayed on a scale ranging from -30 to +30 Newton. Notice that the x force is kept relatively constant around 50 Newton in the -x direction. Notice also the presence of a tangential disturbance force in the -y direction, varying between 6 and 10 Newton. The contour tracking application can be extended to 3 dimensions. Suppose 2 plates, which form an angle of 90 degrees, have to be welded together. weld seam can be tracked using a square end effector as shown. In this application, the task frame consists of 3 false directions, namely the X direction, Z direction, and rotation around the Y-axis, 2 tracking directions, namely rotation around X and rotation around Z, and 1 velocity direction, namely translation along the Y-axis. Again, the application consists of 2 phases: the approach phase, in which the X and Z forces are built up, and the actual tracking phase. In this setup, the distance between the task frame and the motion degrees of freedom of the robot wrist is considerable. As a result, small motions of the end effector require large motions of all robot links. Also, the workpiece was designed so as to allow an assessment of the capabilities, and therefore it includes some short turns which make high demands upon the movability of the robot arm. For all these reasons, we limited the desired tangential velocity to about 10 mm per second. Specification mentioned remains valid for a seam which forms an arbitrary curve in 3-dimensional space. If the nominal angle between the plates does not equal 90 degrees, the task specification remains also valid, but the end effector has to be modified. Stacking blocks or boxes on a pallet constitutes the next task. The general problem can be divided into a sequence of subtasks. One of the subtasks is putting a block or box into a corner formed by 3 faces. In this case, all 6 directions of the task frame are force controlled. Non-zero forces are specified in the translational directions, whereas zero forces or torques are specified in the rotational directions. The desired forces are 10 Newton in X and Y direction and 20 Newton in Z direction. The measured forces are displayed on a scale ranging from -30 to +30 Newton, and the torque scale ranges from -3 to +3 Newton meter. In the final position, the measured forces approach the desired ones very closely. In order to show the enhanced capabilities of a force-controlled manipulator, the Cincinnati robot, which is designed to handle weights up to 40 kg with an accuracy of 1 mm, is now programmed to perform a close tolerance peg into a hole insertion. The peg diameter is only 30 mm and the clearance is 0.1 mm. From specialized assembly research, it is known that the task frame should be placed at the tip of the peg. Zero forces are specified in X, Y, alpha X and alpha Y directions, and the desired velocity of 20 mm per second is specified in Z direction. However, In our experiments, we've added force control in Z direction to avoid large forces. This combination of force and velocity control in only one direction is possible thanks to the particular control technique applied. Initially, the peg has a misalignment of a few millimeters and 2 or 3 degrees. A large vertical force results, which slows down or even stops the insertion temporarily. Meanwhile, the force controller reacts to the very small force and torque measurements and corrects the misalignment. As the misalignment reduces, the vertical force decreases and the insertion continues. The final experiment consists of opening and closing the door of a cupboard. The task is divided into 7 subtasks. The first subtask, insertion of the key into the keyhole, is very similar to the assembly task. The insertion finishes when a force level is detected in Z direction, and the controller then proceeds automatically to the second subtask. While turning the key to unlock the door, which constitutes subtask 2, the robot pushes very slightly in order to keep the door closed when it becomes unlocked. This subtask requires a complicated motion of the robot if the key is not perfectly centered in the robot gripper. After a 210-degree turn, the controller assumes the door is unlocked and initiates the next subtask. Subtask 3 consists of opening the door. The controller has no information as to which side the door opens or what the location of the hinge is. The robot just pulls, and the resulting forces and torques will cause the robot to turn in the right way. A small wire connects the door and the cupboard. As the wire becomes stretched, a Z force is detected and the controller proceeds to subtask 4. In the fourth subtask, the remaining forces are eliminated by specifying 0 forces or torques in all 6 task frame directions. Finally, subtasks 5, 6 and 7, duels of 1, 2 and 3, are performed and the door is closed again. The complete task is now shown again. The sequence of subtasks proceeds automatically without any intervention of the operator.